Okay, now individual photons can have different amounts of energy. They can have different frequencies and different wavelengths. And all of these properties are related mathematically. So if we're taking a look specifically at energy, the higher the energy, the higher the frequency. And so we say that energy is proportional to frequency. As energy increases, the frequency of wave increases. And we can actually calculate that if we insert a constant into our equation, known as Planck's constant. So if we're given a specific frequency, all we have to do is multiply it by the specific constant to get the energy of our photon. That number can be found in your data booklet, and you do not need to remember that. Taking a look at frequency, frequency is inversely proportional to wavelength, so as frequency goes up, wavelength goes down. And again, we can turn this into an equation by adding a constant, the speed of light. So we can calculate frequency if we take the speed of light and divide it by wavelengths. So now I have an example. Say you're asked to find the frequency for red light. The first step is to check your data booklet because the wavelengths for all colors of light is listed. And so you don't need to memorize that. Specifically for red photons, we're talking about a wavelength of 700 nanometers. After that, you just substitute your numbers into the equation and you can figure out your frequency, remembering that c, or the speed of light, is always 3 times 10 to the 8. So you can see me doing the calculations here. We have 3 times 10 to the 8 meters per second divided by 700 nanometers. And if we convert that to meters, remembering that nanometers is 10 to the negative 9 meters, then we get 700 times 10 to the negative 9 meters. If you're just purely looking at either your units, you have meters per second divided by meters. And so our final units should be seconds. To the negative 1, or 1 over seconds, which is what the units that we use for frequency. If you do the calculation, that's what you get. Let's take a look at an example using our second equation. So let's say now we want to find the energy of red light. And so again, we can find our frequency, which we already did previously, and then substitute into our equation, again checking our data booklet for Planck's constant. In this particular case, we're going to have our frequency that we calculated times 6.65 times 10 to the negative 34 joules per second, times seconds, right? And again, the 6.65 times 10 to the negative 34 can be found in the data booklet. If we were to look at units, our seconds cancel out, so we get joules, which makes sense because our energy is measured in joules. Now, this is the amount of joules for 1 photon of red light. Let's say we want to calculate the energy per mole of photons. Well, you know how many photons there is in a mole, so it's simply a multiplication where we take the number of joules, 28.4 times 10 to the negative 20, per photon, and multiply that by 6.02 times 10 to the 23, or the number of photons in a mole, and that'll get us the amount of energy in 1 mole of red light. Now we can also talk about how we can describe not just one photon, but a collection of photons. Just a very quick math graph review. So histograms basically show the frequency or the number of a specific category of things. So you probably in kindergarten polled people in your class, figured out how many people had cats, how many people had dogs, and the blocks represented the number of people. We can do the same thing for photons based on their energy level. And again, remembering that our different colors represent different energy levels, where red is the lowest and blue is the highest. And so again, we can represent blocks to represent, for example, how frequent a photon of red versus green versus blue light is. Now, if we were to include all the visible colors of the spectrum, so a spectrum of colors, again, we could make a histogram showing the frequency or the number of photons in each different category. And what we could get, for example, might be a curve that looks like this, where we're categorizing colors based on increasing energy. And in chemistry, this is known as a continuous spectra. So it shows all of the colors. It's continuous. We see all of the colors in the visible spectrum. Sometimes, instead of seeing all of the colors in the spectrum, what we can get is we can get very specific wavelengths of light that correspond to very specific colors. So in my example, I have very specific colors that correspond to a specific green, a specific blue, and a specific purple. This is known as a line spectra because you only see lines, also known as emission spectrum. The opposite of an emission spectrum is an absorption spectrum, and they look completely opposite as well. Instead of just having particular lines of specific wavelengths, what we can do is we can measure the percentage transmittance, so how much of the colors get through. And what we have is we have 100% of all the colors except for a few lines where we're missing very specific wavelengths. So instead of just colors of specific wavelengths showing and everything else being black, in absorption spectrum we have all of the colors showing except for a few specific wavelengths.